Well, thank you everyone. Thank you, Anka, for that nice welcome. I'm very happy to be here in Bari. It's lovely, a little warm, but I'm enjoying my time. And I found an awesome gelato place. It was listed on Saviero's information. Tested it out yesterday on my first day. So I first wanted to say it's a great honor to receive the George Brown Award. As a student and young researcher, I relied on some of his work on crystal structures of clays. That was really essential. And when I was reading up on him, I was sort of happy to see that he was actually a chemist, because in most of my work I work with geologists, and there's no problem with geologists. They're fine too. But yesterday, actually, at the welcome party, I met several chemists too. So maybe there are more chemists involved in clay mineral studies today. In any case, that was something I shared with George Brown. And his first research project was studying the exchangeable cation sites in montmorillonite. And this was so exciting to me, and I wish I'd known all this earlier, but I just found that out in the last couple weeks. That was exciting. And some of the things he's most admired for are his scholarship, his clarity of thought, and his vast knowledge of clay minerals. And I think that's something that all of us here should aspire to. So I enjoyed seeing that. What I'm going to talk about today is remote detection of minerals, especially clay minerals on Mars. That's sort of the focus of my work. And then I'm going to talk about how we do that using remote sensing, and how spectroscopy works, especially visible near-infrared spectroscopy, and especially for clays, which kind of bands we use to detect that. And then the importance of analog sites and how we study clays in the field in order to inform detecting clays on Mars and other planets too. And then finally, coordinating the lab field theory and modeling in order to really understand, when you're studying planets, they're far away, so there's always a little bit of guessing, inferring, hoping, and we don't have quite as many toys in the lab as most of you do. So we have to put together the data we can. So we now have confirmation that there are phyllosilicates on Mars. And in fact, there are oodles of phyllosilicates. There are tons of clays and all kinds of clays, and that's really interesting. But for a long time, that wasn't really accepted. In the 1970s, NASA sent a couple of Viking missions to Mars, and they found basalt, and they looked at the chemistry, and they said, oh, hey, the chemistry is very consistent with clays forming. Probably that's what Mars is composed of, altered basalt clays. But through the years after that, there were telescopic observations, and they never saw any features consistent with clays. So people were saying, And mostly physicists were studying spectroscopy and remote sensing of stars and planets and other bodies. And to them, it's sometimes just check a box and, oh, nope, that's not there. Okay, look for the next thing. And so they didn't have the sort of geologic perspective that the scientists working on the Viking missions did. So there ended up being lively discussions during my PhD studying clays as a Mars analog. So I would tell PhD students today, you may have a great idea, and there may be people who don't believe you. And you may have some animated conversations at conferences, but don't necessarily back down. If you think you're right, stand up for what your data shows. And so for a long time, I was the one person thinking there were clays on Mars, or one of a handful. And now everybody knows, of course, there are clays on Mars. There are oodles of clays. So it's nice to see that we've come there. And ESA's Mars Express Omega imaging spectrometer first really confirmed that clays were present, but it was looking at sizes about 1 kilometer per pixel, which are huge. And CRISM, NASA's imaging spectrometer on Mars Reconnaissance Orbiter, looks at smaller sizes, still rather large compared to field sites 20 meters or 100 meters, and you're averaging together a lot of space. But now we definitely can characterize these clays and their assemblages. So how does remote sensing work? We need a radiation source, and we need a surface, and then we need a detector. And our eyes work well as detectors, so everything we're looking at, where we have the sun or another light source, it's reflecting off a surface, and we're detecting that in red, green, and blue. And with these imaging spectrometers, we're collecting data from an image, not just in red, green, and blue, but in this case of PRISM, 544 channels. So for these example minerals, a sulfate, gypsum, nontonite, or olivine, we see different kinds of spectral shapes. So there are these bands and dips, and we use these as a fingerprint to identify minerals on Mars. And so across the planet, here's an image of Mars with Valles Marineris here. Here's Valles Marineris. There are a lot of, there's a lot of sulfates here. This is the code at the bottom. Phyllosilicates are in blue, and phyllosilicates are observed all across here. It's sort of the southern part of Mars. We see the ancient surface, and you can see all of these impact craters. The northern part is covered with dust and sand, and it's harder to see below, so it's sort of a mystery still. We don't really know what that surface is. And if we zoom in at some sites, this is a place called Mare Vallis, and we see all of these light tone areas have phyllosilicates. And this is about 100 kilometers across. And each of these PRISM images is about 10 kilometers across for scale. So we map these phyllosilicates and friends, their associated mineralogy, in different colors in order to see them in the terrain. And one of the most common phyllosilicates on Mars is what I termed iron magnesium smectite in a science paper back in 2008, and now everybody calls it iron magnesium smectite. And unfortunately, we don't really know if it's dioctahedral or trioctahedral, but it's a smectite including iron and magnesium. And so looking at this particular spot in Mare Vallis, we look at these spectral shapes, and we have a water band here, and then we have OH bands here, and these change depending on the cations and octahedral sites. And so there's a lot of this iron magnesium smectite. Sometimes there's some ferrous clays and some acid alteration or sulfates, and then we see aluminum-rich phyllosilicates and then some nanophase materials at the top. And in other places, we see smectites mixed with sulfates. In this area, we have some sulfates on the other side. So this is in part of Valles Marineris. It's called Ias Chasma. We have sulfates on the side, and there's a breach in this mountain, and some sulfate brine sludge oozes over the top. And then there are some smectites here that got altered, and I used some work that Jana Marajova did a while ago with acid-treated smectites to inform what we think is happening here. And I saw she's here, and I'm hoping to talk to her about that a little bit. But we see this doublet in the spectra that's not like the aluminum smectites or the iron smectites, and so we think it's acid-treated smectite. The other major kind of phyllosilicates we see on Mars are more high-temperature clays. And this is a place called Terrena Terra on Mars. It's between two giant impact craters. And there are smectites that formed initially, but then they're altered to chlorite smectite and chlorite and also zeolite. And so again, we fingerprint these minerals with these spectra, and of course they're much noisier than lab spectra, but for all of us spectroscopists looking at these spectra are beautiful and amazing, and you probably don't see that. But when we're looking at much noisier spectra or telescopic spectra of the whole planet or many kilometers, this is really a huge step forward. So stepping back to the lab then, how do we identify clays or other minerals with visible near-infrared spectroscopy? So some of you are infrared spectroscopists, probably you know this already, but for those of you who aren't spectroscopists, I just wanted to walk through, this is an example spectrum of montmorillonite, doped with magnesium in this case, and we were looking at spectra measured under ambient conditions and spectra measured under moist, humid conditions, and I marked the water bands in blue and the OH bands in green, and these are combinations and overtones. So there's a symmetric stretch and an asymmetric stretch and some bending. So these mid-infrared vibrations are then added up in combination bands or as overtones. And when I was studying spectra of clays back in the 80s and 90s, people were mixing up OH and water, and there wasn't a lot of work on this in near infrared. And so I did a lot of work under different moisture levels to try to figure this out, and especially for smectites, because of the interlayer region, the amount of water depends on the type of cation and how humid it is. And so we were able to use that to help figure this out. So again, for the OH, the structural OH, those band positions depend on the type of cation, if it's aluminum, iron, or magnesium. And those are these green bands here. And then for any surface, you're going to have water molecules that are adsorbed on the surface if it's a charged surface, and then there'll be sort of the first layer and outer layers. So that's also happening with clays and with smectites in the interlayer region as well. And so for part of my PhD, I was trying to connect the mid-infrared spectral features with the near-infrared features and sort out exactly which ones were bound in the system. So the light blue here is actually bound water in the structure, or the first layer in the exchangeable region, and then these dark blue regions are for this sort of outer sphere. And I just checked recently, so this is one of the first papers I published, and it's part of my PhD, and now there are 476 citations. So it's nice that people read your thesis or care about what you did as a grad student. So that was interesting. So one of the things that's important for Mars or other planets when we're trying to detect different types of phyllosilicates is looking at the position of these OH bands in the octahedral sites, connected to the cations in the octahedral sites. So if we look at montmorillonite and nontronite, for example, we see this difference in the peak positions, and saponite or hectorite would be slightly longer wavelength than the iron. And if we look at serpentines like chrysotile, we see magnesium OH band, and camazite we have iron 2+, and also a combination of aluminum and various iron. And also micas have multiple cations, and that gives you multiple bands in this region. So something I've done with other minerals too, this is a carbonate study, is look at the bands in the mid-infrared region, so the stretching and bending vibrations, and then in this case these are both calcium carbonates but with different structures, and I looked at different grain sizes and then figured out the band assignments for these combinations and overtones. And for clay minerals there's not quite so much going on, but still you can look at the stretching and the bending vibrations and then combine these for the stretch plus bend and multiply this by 2 and an offset factor to get the overtone. So by looking at the mid-infrared and the near-infrared together, we could confirm that what we're looking for is actually there. So when you're looking at planets, you have to really be sure that the spectral features you're looking for make sense physically. And there's some, there was a paper in 1990 where some people from the USGS announced, oh, we found scapolite on Mars, which is a really strange double carbonate mineral that no one's heard of. Well, they were wrong. They were identifying prehnite that had a little bit of scapolite in it, and they were just doing what we called Sesame Street spectroscopy, which one looks like the other. So it's really important to know what your spectral features are due to and make sure that when you're identifying something on a planet that it makes sense in the lab as well. And so back again to using this water and OH spectral features to identify clay minerals, we're looking at the structures of the clay minerals and the cations in these octahedral sites, and also the cations in the exchangeable sites and how they affect the water that's in that region. So on a lot of these nanophase or amorphous particles, you're going to see water molecules bound there, and in the inner sphere region you're also going to see a cation with inner sphere and outer sphere water molecules, and that's something we can also look for in remote sensing. So moving on to analog sites, we look at a variety of analog sites in order to try to understand potential formation conditions on Mars. So Mars today is a very cold and arid planet, and we think that it was warm and wet in the earlier time period, what's called the Noachian age, because of all of the smectites that cover the surface. And so I spend a lot of time in the field looking at altered volcanic tephra. Usually we try to go to places where there aren't a lot of people and garbage and plants. We try to look for just the rocks, and also pedogenic sites, and the Painted Desert in Arizona is a good example of that. And also the Antarctic dry valleys are a great example of cold, dry deserts. So these are some examples of the field sites. In almost all of these you see a lot of rocks and not a lot of plants. Here there are some plants too. So we try to avoid those. And so looking at these outcrops, I'm always interested in the spectroscopy primarily because we connect that with the remote sensing, but I work with a lot of colleagues with expertise in SEM or XRD or other kinds of techniques in order to characterize the samples as best we can and understand the clays and the related mineral assemblages that are present. So a number of these sites from the Hawaiian Islands have smectites and also silica and some sulfates. So in the Painted Desert, this image didn't quite turn out how it was, but what I wanted to show at this Painted Desert site, it has these horizons. One of the places where we see the most clays on Mars is called Marth Vallis, and it's the same for 1,000 or maybe more than 1,000 kilometers, where they have layers of these phyllosilicates. And one of the places where I've seen something similar is at the Painted Desert, where you see these layers of clay-rich material. I think there's some smectite and some kaolinite, some iron oxides, and some carbonate there. And there's one point that the rangers took me to, and it has gypsum and jarosite and montmorillonite together in one site, and that's something that we're also studying in some places on Mars where clays and sulfates are together. And so here you have these horizons of different clay minerals and then pockets of sulfates as well. And finally, in the Antarctic dry valleys, there's not a lot of clay formation. It's mostly poorly crystalline materials, so it's very cold, of course. The sediments contain feldspar, pyroxene, and quartz. And there's some trace amounts of mica, actinolite, and in some subsurface areas, some gypsum, halite, and some poorly crystalline materials, and some carbonate. So some of these cores, I haven't been there. I would like to go there. Maybe one day. Maybe some of you've been to Antarctica. Colleagues of mine at NASA Ames have been there, and they generously shared some of their samples with me. And so from some of these lakes, people cut holes through the ice. It's several meters, and dive down through the oxic water and anoxic water and collect samples of sediments along this border. And so we've been characterizing the mineralogy, and these clay-like zones don't ever have smectites. Instead, they have sort of poorly crystalline aluminum silicate phases. So comparing this with studies that colleagues have made from other glacial sites, we don't see smectites forming in these really cold environments. Instead, we primarily see these poorly crystalline aluminum silicate phases. So then, putting this all together, coordinating lab field theory, modeling, remote sensing, in order to understand what we see on Mars, I think of this as sort of a puzzle. So we have orbital data that we use remote sensing for. We have rovers on the surface, and the rovers can provide a lot more data, and it's up close, but only the instruments that they've sent. And it seems that NASA at least sends different instruments on each mission. So they tend to have an instrument that measures chemistry on each mission, but sometimes they're measuring Mossbauer, which is great because you can characterize the iron. And sometimes they're measuring Raman, which is also useful, and sometimes they're measuring X-ray diffraction. But each mission is measuring something else. So you're comparing apples to bananas to oranges, when you're trying to compare data from different places across the planet. And the only way that I see to really coordinate these is through the remote sensing, because we're measuring the whole planet at not really close scales, but 20 to 100 meter scale with visible near-infrared spectroscopy. And so through field analyses and lab analyses where we're measuring the visible near-infrared spectra that we need for the remote orbital detections, we can also then bring in the different toys that are on each of the different rover missions. So to try to connect data from rover 1 to rover 2 to rover 3, then if we can do studies at field sites, then we can try to bring these together. So the goal of a lot of the field work then is to characterize analog sites with as many mission-like instruments as you can. And so sometimes you're able to bring these to the field, which is great, but often it's difficult to bring like an SEM. I don't think there's an SEM that can go in the field yet. So of course those samples have to be brought back. But we're studying volcanic sites in order to determine alteration in different potential early Mars environments. There's also a big discussion in the Mars community. The atmospheric modelers are having a really difficult time modeling the conditions necessary to have liquid water on the surface, not even the warm water necessary for making clays. And so we still have these discussions at conferences sometimes where they're like, we don't know. I mean, the geologists are always saying it was a warm, wet planet, and the atmospheric modelers are saying we can't get there. So we're not, we don't believe that it was a warm and wet planet. We see water features and we see mineralogy that indicates it was, but we can't get there. And so we need to study field sites in order to try to understand what might be happening. And a lot of lacustrine and pedogenic outcrops in the field provide examples of smectites and the assemblages that we see. So smectites mixed with carbonates and smectites mixed with sulfates. And especially these evaporite settings produce salts and mixtures of phyllosilicates with gypsum or other sulfates that we observe, or halite. And then looking at the cold desert environments provide a potential for understanding the chemical processes that are taking place now, and probably for the last long time. So on Mars, we think about 4 billion years ago is when the planet was warm and wet. So 4 billion years is a long time. And when you think about when life evolved on Earth, we don't really know when that happened, but we see fossils that show life was here about 3.5 billion years ago. So on Mars, it appears that about 4 billion years ago we formed these clays based on dating of the estimates of the date of the surface from crater counting. So then we use lab studies as well to coordinate the data from the field and try to perform experiments. So brine reactions with clays, for example, to see what would happen, or brine reactions with basalt to see what would happen and how can you form clays. And of course, on a geologic scale, it would take forever, so you have to always change the conditions in the lab to produce results you can observe in a timely manner. So coordinating all of these is what I try to do and what my group tries to do. And a recent paper from 2018 looked at what are the temperatures that we would need in order to form these smectites, to try to help the modelers to try to bridge this gap of maybe Mars was never so warm versus Mars had to be warm, and to try to figure out how that could have formed. So we looked at places like the Columbia River basalts where there's a lot of montronite in Idaho in this particular area, and looked at the temperatures and the timelines for this. And there's always the temperature in the summer when it's hot versus the mean annual temperature. So modelers use mean annual temperatures, which is sort of tricky to figure out when you have diurnal variations and also annual variations. So, and then my colleague Louise Gago-Duport used some laboratory modeling in order to determine how fast nontronite would form in plausible environments at different temperatures. And so his analyses showed that down around 0 to 5, 10 degrees Celsius, there's not a lot of not a lot of nontronite forming or other smectites. But once you get up to 20 degrees, it forms a lot faster, and 40 degrees much faster. And so this is comparable to what we see from the field, where we look at a lot of volcanic sites where smectites form. They're usually pretty warm, and they have wet-dry variation in the water. And so it's not consistent water, it's wet-dry cycling. But glacial environments in Iceland and in Oregon and in Antarctica, they're not forming smectites. So at 0, 5 degrees, and this is probably common knowledge to all of you, but for the Mars community, they're like, oh, there's liquid water, the minerals will form. But it's important to also think about the temperature of the water. And so we calculated some rates for formation of this, and we determined that it wouldn't have to be warm and wet for billions of years or even hundreds of millions of years, maybe just 1 to 5 million years, which is still a long time, but when you're thinking about the formation of a planet, and it could have been that it was pretty cold in the early times, but there were these sporadic times when the planet was warm, and that during these sporadic episodes of warm conditions, then these smectites formed. And what's interesting to me is this iron magnesium smectite is found pretty much all over the planet. And so I think that during this early Noachian time, conditions must have been pretty similar planet-wide, and that since then there were obviously variations. And these short-term warm and wet environments may have been what formed these smectite clays in an otherwise cold environment. And then around 3.8 billion years, probably a lot of that changed. And there's going to be a talk later this afternoon from the smectite, the clays at Gale Crater. So hopefully we'll hear an update on that as well, for those of you interested. So this is one site called Marth Vallis that I presented before. There are these phyllosilicates here that formed mostly in a warm, wet environment, and then there's this channel where water flowed through, and then you can see outflow channels here. So after this early episode of warm water, there was a lot of cold water flowing on the surface that was cutting through these. And what I think is interesting is that these cold water channels cut through the rock and cut through the phyllosilicates, but they're not, there's no evidence that they're forming more clays, they're just cutting through these. And so that sort of bolsters the idea that there was warm water to form the clays and then cold water later forming these valley networks and outflow channels that look something like rivers on Mars. And these could have been very short term. You could have had ice that melted and gushed that water out and then it was gone, but it could have been enough to carve through some of these features. Let's move on. So coordinating these lab field remote observations helps us understand the kinds of clays that form, or how this iron magnesium smectite forms, but then also how do we get the regions that form these high temperature clays, the like chloride and serpentine, how do you get temperatures in 100 or 200 degrees to form these high temperature clays? And so some of these could be formed subsurface. And in this particular area I'm studying called Terrena Terra, there are two giant impact craters on the border, and then this area in the middle. So what we expected was near these giant impact craters, we would see a lot of high temperature clays, and then in the middle, we would see low temperature clays. Well, we kind of see the opposite, which made us kind of wonder for a little while, well, why is that? How come these impact craters didn't form high temperature clays? Well, it appears that there are a lot of there's a high geothermal flux in this area. So a colleague of mine, Muhu Oja, has been characterizing the geothermal flux. And so this is, these blank spots here are these impact craters. And then in the middle are where clays have been detected, and it's also a higher, warmer, the yellow colors versus blue means higher geothermal flux. So for whatever reason, it could be radionuclides or it could be volcanic. There's a higher geothermal flux in this central region, or maybe it does have to do with the impact somehow, but we're not seeing the high temperature clays near the giant impact craters. Instead, we're seeing them in this central area. And so we use a number of different mapping techniques. This one is PRISM at low resolution, but higher coverage. And then we use these small images to get targeted data at the 18 to 20 meter resolution. And so again, we're looking at smectites in sort of a purple tone, chlorite smectite in pink, and chlorite in red, and then zeolite is mapped in blue here. And the green is basalt. And so mapping these really helps us see where the different minerals are present on the surface. And one of my favorite things to do is go visit my colleagues in Berlin at the DLR, and we take the PRISM compositional data and overlay it on the high resolution stereo camera data from the Mars Express mission, and then we can see the mineralogy over the geology and the terrain, and that's much more powerful for understanding. So in terms of Martian phyllosilicate environments, there's sort of a Mars aqueous alteration timeline. We have layered surface clays, like at Mars Vallis and other places, where during what's called the Noachian, this timeline about 4 billion years ago, we see emplacement of basaltic rocks and ash, and maybe about 4 to 4.5. And then right at about 4 billion years, or 3.9, we see formation of these iron magnesium smectites, and likely in neutral or mildly alkaline conditions, and potentially intermittently warm 20 to 30 degrees Celsius periods in an otherwise cold climate. And following that, maybe about 3.8 billion years ago, during the Hesperian, we have a lot of salty brines and evaporites resulting, and sulfate emplacement on top of the smectites. And then at Mars Vallis, at least, there's another episode of a warm and wet period that produced aluminum phyllosilicates, and potentially more acidic since it's following the time when sulfates were formed. And then in the later Hesperian time frame, we see these short-ranged ordered phases, allophane, ammogalite, and similar, and these are forming probably in a cold or water-limited environment based on analog work from Antarctica and glacial environments. And interestingly, when you compare this with the results from Gale Crater, where they sent an X-ray diffraction instrument, they see huge amounts of this poorly crystalline X-ray amorphous material. So it's not just 20 or 30%, that's the minimum that they see. They see 70 to 80% in many areas. So that's something that we had no idea about until we sent X-ray diffraction. So that was a huge step forward in our understanding. So there could have been a lot of alteration on Mars under cold environments where only these poorly crystalline phases were found. And then we have high temperature phyllosilicates forming that are probably less connected to the surface environment and more connected to the subsurface, where diagenesis is occurring due to geothermal flux from radionuclides or from volcanism, and also acute high temperature events from impacts or active volcanism. So sort of a summary of this again, at places like Mars Vallis, we see these huge layers of smectites, and we see these horizons where you see different kinds of clays and other mineral assemblages on top of each other. And we see places like in Valles Marineris, at Eos Chasma, and others where we have sulfates and phyllosilicates together. And then we see high temperature clays at this region called Terrana Terra, which is also near Jezero Crater. So Jezero Crater has smectites and carbonate, but it also has, in the nearby area, high temperature clays like serpentine and chlorite, and in some places talc and prehnite, so some really high temperature clays. So from Marth-Vallis, this is an example of how we estimate the presence of these minerals. The red is the iron-rich smectite, the blue is the aluminum-rich smectite, and the green is this allophane or poorly crystalline phase. And what I like to do is make these 3D surface views and then rotate them, and that helps me see the stratigraphy of which one is on the bottom and which one is on the top. And this is the site in Terrana Terra, and here, you know, these colors are a little wild. The green is the basalt, and the blue is the zeolite, and then red is chlorite, the high temperature version, and pink is more of a smectite chlorite, and more purple tones are the smectite. So you see all of these, and we use impacts like at this site. There's this double crater site that has a lot of phyllosilicates, and these are our road cuts. Obviously, we don't have anybody with tractors building roads on Mars. Instead, we use these impact craters, and the phyllosilicates are, in many places, they're not right on the surface. So in Marth-Vallis they are, and in some other places, but like in Valles Marineris they are. But in a lot of areas, we need these impact craters to throw out the smectites from the ejecta. So one of the big questions that NASA's interested in is life and habitability. And so where do we go on Mars to find if life might have been present? Where do we send the rovers? Where is a habitable site that potentially could have been colonized if life were there? And so we use the remote sensing data to guide decisions on where the rovers should go. And probably a lot of you study phyllosilicates, and maybe some of you study origin of life. But there are a lot of phyllosilicates during this Noachian period, and in particular smectites that I've been talking about. And there are people studying origin of life on Earth, and in fact there was a whole book written on clay minerals and the origin of life. And a lot of people think that an iron smectite similar to nontronite was present on early Earth and may have been involved in origin of life. So these hydrocarbons and ammonia are present in a lot of icy bodies in our solar system, and comets distributed this throughout our solar system and elsewhere. So hydrocarbons and ammonia should have been abundant on early Mars. So one of the questions is, where are they now? How come we don't see them? And we don't have a good answer for that yet. One answer is that solar rays are bombarding these, that Mars doesn't have a thick atmosphere, it's a thin atmosphere, so it's not as protected as we are. And we do actually see hydrocarbons and ammonia on other bodies, including Ceres, which is an asteroid. And one reason smectites are so interesting, and probably a lot of you even perform organic reactions on smectites, and I think this is one really interesting ability of smectites, is to have this sort of template with a charged surface to grab molecules and hold them in place, so that if they want to, they can get together and form maybe the molecules necessary for forming life. So we have this iron magnesium smectite that's maybe 100 to 300 meters thick on a lot of the planet. And even if this was there for a short term, this could have also collected some organics. So if we actually go to one of these sites, we might find hydrocarbons or maybe interesting molecules here. And then high temperature phases could have been forming through geothermal processes and might have sort of kept the subsurface kind of warm and happy, and then been a place where microbes could have continued later. So I think that's the end that I wanted to talk about mainly, and I just wanted to thank again the Clay Mineral Society, and greatly appreciate the George Brown Award. And my time is 39:19, so yay. Hopefully it will keep us from getting too far behind. Thank you so much.